Hello everyone. It is with great pleasure that I welcome you back today. And today we're going to be looking at rotational kinematics. Okay, just a very quick recap from last video. So we said, if you recall correctly, we have a couple of new units. Okay, they're not really new, but I want you to think of it in terms of alternate units. So linear, and now we have angular. So in the past, okay, we saw certain quantities. So we saw, for example, distance, and that was, of course, measured in meters. Okay, now angular, it is symbolized theta. It's the same thing. I want you to associate it the same exact thing as simply distance, but theta is now simply going to be given in terms of rad. Okay, and we saw from previous video, it's 2 pi rad over 360. That's how you convert from degrees into radians and vice versa. The next one we saw when we talked about linear is velocity. And we saw the velocity is meters per second. Okay, so the new angular quantity that we gave for that is omega, and that was, of course, it's going to be rad per second. And for linear, we also used acceleration, that's symbolized with an A, and the units were meters per second squared. But now we're going to be using a different quantity. It has a very similar symbol, that's an alpha, and that's of course going to be in terms of rad per second squared. So so distance became theta, velocity became omega, and A became alpha. Okay, so we can plug these new terms and we can actually now derive brand new equations, but you can still think of them as the same. So let me just go ahead and erase this, and let's go back to our PowerPoint. So here is our PowerPoint. This is where we had stopped off last time, and this is where we are. Okay, so if you recall correctly, for velocity, okay, I'm gonna get out of it so I can show you. So for velocity, we said it was VF equals velocity initial plus acceleration times time. For distance now, we can actually reformulate this. So distance equals average velocity times time, and average velocity, of course, we gave it as 1/2 velocity initial plus velocity final. And then we saw this equation right here when we did linear kinematics, and we saw that VF squared equals velocity initial squared plus 2 times A times D, which is the distance. We call this, if you recall correctly, the timeless equation. And of course, the last one was the distance acceleration formula, and we said that was d equals VIT plus 1/2 AT squared. So now, all these formulas right here are now going to be changed just slightly. So if you use the connotation that I showed you earlier, so for V we use omega, for A we use alpha, obviously T doesn't change, that's simply time, and for X, which is distance, you use theta, we arrive to the following new equations. So the first one is the acceleration formula. So velocity final equals velocity initial plus acceleration times time. This is distance equals average velocity times time. This is now our timeless velocity final squared equals velocity initial squared plus 2 times A times D. And notice how the velocities are now replaced with omegas, velocity final, velocity initial. Alpha A is replaced with acceleration, and distance, of course, with theta. And then finally, our very famous distance acceleration formula, d equals VIT plus 1/2 AT squared. Distance is replaced by theta. Velocity initial is with omega naught. Times time plus 1/2 AT squared. And of course, that's acceleration, and that is time. So, based on what we know, I believe we are ready to see our first formula. But before we go into that, I want you guys to see them side by side. This is what I was talking about earlier. So our acceleration formula became this. So for velocities, we used omegas. For distance, we used thetas. This is our distance acceleration. This is our regular linear equation. This is our rotational motion. And this is, of course, is our timeless. So with that said, we can go ahead and we can do our first problem. So the problem says The blades are whirling with an angular velocity of positive 375 rad per second. So as you can see over here, it's positive. So what does that mean? That means it's going to be counterclockwise. So this is rotating about the axis of rotation. When the blend button is pushed, the blades accelerate and reach on a greater angular velocity after the blades have rotated through an angular displacement of positive 44 rad. That means it's in the same direction, but the distance now, because remember, angular displacement is distance, is 44 rad. So the angular acceleration has a constant value. So this angular acceleration, 1,740 rad per second squared. They're asking us to find the final angular velocity. In other words, they're asking us to find the final velocity. Now, I want you guys to look at all these terms right here. Do they give us time? No. So obviously, we would have to use the timeless equation. So let's go back to our trusty sketchbook, and let's first write down the variables. So we said the initial velocity, so omega initial is going to be 375 rad per second. That's our initial, okay? And our distance, our displacement, our angular displacement, which is a distance, it is going to be positive 44 rad. And our acceleration, now our angular acceleration, that is going to be 1,740 rad per second squared. And they are asking us to find the final angular acceleration. Okay, so that is what the problem is asking us to do. So obviously, just like we just said, we would have to use, okay, the timeless equation. So if you recall correctly, everybody should remember this. It was Vf squared equals Vi squared plus 2 times A times D. So now these terms now become omega final squared. That's our final velocity. Our angular initial velocity squared plus 2 times our acceleration times, and our distance now became theta. So as you can see, it's exactly the same formula with just a couple of different variables. So the only thing we do now is we plug things in. We're trying to find final angular velocity. So that's going to be our unknown. So our initial velocity, that's going to be positive 375 rad per second. And please do not forget to square that. Positive 2 times the acceleration. The acceleration is given by this value right here. So that is going to be 1,740 rad per second squared, and times now the distance, the angular displacement, which is simply 44 rad. So now, when we square this, and we add it to the double of the acceleration times the angular displacement, and then finally we take the square root right over here. I think we've done enough problems in class. I'm pretty sure you guys, can do this on your own. You can pause the video and do this on your own. But I think everybody would agree that we're going to find about 540-ish, 542 rad per second. And let's just double check. And here is the problem. So we said 542. Notice how it's rad per second, meaning meters per second. And if we look at this, it is 542 rad per second. Thank you very much, everyone. That's our first angular kinematic problem. Thank you.